Hi, welcome to the lecture number 53 of fuzzy sets, logic and systems and applications. In this lecture, we will continue our discussion with the remaining part of the Mamdani fuzzy model. Here, let us understand the fuzzy reasoning of Mamdani fuzzy model for the following. Mamdani fuzzy model using max-min and max product compositions for fuzzy and crisp inputs for multiple rules with multiple antecedents. In the previous lecture, what we have done was the Mamdani fuzzy model using max min here, max min and max product compositions for fuzzy as well as the crisp inputs for single rule with single antecedents and single rule with multiple antecedents. Now let us discuss the third scenario where we have a Mamdani fuzzy model with multiple rules, more than one rule, and even in the rules itself we have multiple antecedents. So let's now discuss this scenario. So here we are taking, for simplicity, we are taking two rules only under this multiple rule case. With multiple antecedents, here also we are taking only two antecedents. So let me just make it very clear that we have this as the first antecedent, and then we have the second antecedent. And we have two rules. So two rules, two antecedents. And we all already know that this is the premise part and this is the consequent part. This is premise part, this is consequent part. And here also we see that premise part is fuzzy and the consequent part is also fuzzy. So both premise and consequent, both parts are fuzzy. When we say fuzzy, it means we have this premise and consequent, both parts are designated by the fuzzy values. Like here in this case, A1, B1, C1, A2, B2, C2 are fuzzy values. Now, let us, on the same lines as we have discussed the two previous scenarios, let us discuss this also. So here we have rule number 1 where we have x is a1, y is b1, is x, is y, is z. X, y. This is rule number 2. So we have two rules and then two antecedents. So first antecedent is this, second antecedent is this. And these two antecedents are connected again by AND. You can see here, AND. So both the rules are containing AND as the connectives. Now, these two rules are given in the fuzzy model, Mamdani fuzzy models, or in other words, we can say this Mamdani fuzzy model is described by or characterized by the two fuzzy rules. And these fuzzy rules are with two antecedents, and which is clear case of the multiple rules with multiple antecedents. So let us first take the fuzzy input. So rule 1 and this is rule 2. So here let us take the same input here x, y, and x is fuzzy, y is also fuzzy. When we say fuzzy, again fuzzy means a fuzzy value, and fuzzy value is always characterized by represented by a fuzzy set. So we are taking a fuzzy set. Alright, so now let us apply this input to the fuzzy model, and let's see what we are getting as the output to the corresponding input. So this is fuzzy input, first fuzzy input. So here x is the fuzzy input, and what is this fuzzy set here? Fuzzy set a dash. Here y is again is also a fuzzy set, which is b dash. This is y. Alright, so now let us apply this. So this is very simple, and as we have done in second scenario, so let us take the rule number 1 first and take these two x, y fuzzy values, superimpose, and then find the points of intersection, and these points of corresponding to the points of intersections, the membership values will become the w's, like w1 and w2, like this here. So when we superimpose, this is our rule number 1 and this is rule number 2. So when we superimpose a dash, so you see here a is superimposed on a1, b dash is superimposed on b1. So a dash is superimposed on a1, and we are getting here as the w1. Here also we are getting the point of intersection as w1. Now here in this case, since we are using the max min composition, so now let us take w1 is w2. So let us take the minimum of the w1 and w2, and when we take minimum of the w1 and w2, we are getting w as 0.36. So this is w1, this is w2. So w is, so let us take this as the w dash, this is also w dash, and when we take this as the w1 and w2, w1 dash, w2 dash, let us call this as w1. 1 is for the rule here, this is for the first row, first row is for the first row. So when we get w1 here as the minimum of the w1 dash, this was the w1 dash, this is w2 dash. Alright, so w1 is coming out to be 0.36, and again we use this w1 to truncate c1, and this is the output, is the fuzzy output corresponding to the fuzzy inputs. The fuzzy output from rule 1, from rule 1. Rule 1. Similarly, we do the same exercise using min composition. Here also we are getting W1 dash, W2 dash. When we take W1, W2 dash here, in this case, so when we take min, because we are taking max min composition, we take min, so W2, which is the outcome, which is corresponding to the second rule, so W2, with this W2, we truncate C2, and this becomes C2 dash. So this we can write as the fuzzy output from rule 2. Now here we are using max min composition. So min is utilized here. Now whatever outcomes that are coming from each rule, we are taking the maximum of it. Maximum means we are taking the union of it. So let us aggregate it with union. So when we take the union, so we are getting this kind of thing. You see here, when we plot it, we are going to get the union. See here. So we aggregate the output from rule 1 and then we get the output from rule 2. Both the outputs are aggregated. We are taking the union, and the union is giving us, see here, the max is giving us the fuzzy output corresponding to the fuzzy input. Now this fuzzy output can suitably be defuzzified by using suitable defuzzifiers. Now in this scenario, the third scenario, let us see when we use the max product composition. So this is again very simple. Here when we superimpose the fuzzy inputs here, so A1 is superimposed to A dash is superimposed to A1. This is W1 dash, this is W2 dash. Similarly, this is W1, W2 dash. So since here we are using the max product composition, so we take the product of these two. So product is going to give us 0.31, and this is the output of the rule, output from the rule, fuzzy output that we are getting. The fuzzy output from rule 1. Similarly, here also we are getting some output on the same lines. Here also we have the W1 dash, W2 dash. When we use max product composition, so we take product, in this case product of W1 dash, W2 dash. So when we do this, we are getting here W1 dash, W2 dash, and yes, these are small x, small y, small z, small x, small y, small z, small x, small y, small z, everywhere. Small x, small y, small z. Small x, small y, small z, small x, small y, small z. small x, small y, small z, small x, small y, small z, small x, small y, small z. Alright, so this way we are getting the again now coming back to the third scenario, when we use max product composition. So in max product composition, we take here again the product of the W1 dash W2 dash, and this truncated portion becomes the and we truncate with the value W2. So this is W2 here, W2, which is nothing but 0.20, and here W1 is 0.31. So this way we are getting two outputs. The first output here is corresponding to rule 1, and the second fuzzy output is corresponding to rule 2. So here I can write fuzzy output from rule 2. So every rule is going to give us some output, but these rules should be applicable. So this way when we take the max, so here we take the union of this, means we take the maximum union, right? We aggregate. So when we do this, we are getting this structure. This is fuzzy set, fuzzy value. So this, as we can see, is a fuzzy value as the output corresponding to the fuzzy inputs. X is A dash, Y is B dash. So we can call this as the fuzzy output, and this can be suitably converted into crisp value by using some defuzzifier. Now here we have discussed when x, y both were fuzzy values. Now let us see what happens when we use x, y both are crisp values. Means the inputs that are fed are crisp values. So let us go ahead and see. So here we have rule number 1, here we have rule number 2, and we see that when we take x is equal to 7, means x, the value of x is 7, the value of y is 6.5, and here please note that all these x that we have written here is small, small x, small y, small z, small y, small z. So this is rule number 1, rule number 2, and we see that we have two antecedents here. Both the antecedents are connected by AND. Here also we have small x, small y, small z, small x, small y, small z. Now here we see that we have these inputs, the values of the inputs x, y are crisp values. So I can write here the values of x and y here are crisp values. Okay. So when we have crisp values, now we apply these crisp values, and when we apply this, we see if there is any intersection here on A1 for x is equal to 7. So we see that we have one intersection. So we call this as W1 dash. Similarly, for y value, we see whether there is any intersection here. Yes. For y is equal to 6.5, we have on B1, we have W2 dash. And similarly, for rule 2 also we see. So here also we see that we have the intersection W1 dash, and then we have the W2 dash. Now for the first rule, first, so we are taking the max min composition. So we'll take the min of W1 dash and W2 dash, min of W1 dash, W2 dash, and this is going to give us W1. So let's see what we are getting here. When we take the min, we are going to get, obviously, the min W1 is going to give us W1 dash, which is nothing but 0.28. W1 dash, which is nothing but 0.28 here. So here we see that W1, which is the strength of this rule, is the 0.28, and with this value 0.28 we truncate C1. C1 is the consequent part, so we truncate here. Here also we write all small. Alright, so this is the output of the first rule corresponding to the crisp inputs x and y. So the output from rule 1. Similarly, when we for the second rule, we are getting this as the output, the fuzzy output after truncation. Here so this is the output from rule 2. Now since here we are using max min composition, so we have to take the maximum of all the outputs. So we take the aggregation, we take the union of these two outputs coming from the rule number 1 and rule number 2, and this way we are getting this structure, this fuzzy value as the output corresponding to the inputs as crisp values. X is equal to 7 and y is equal to 6.5. So this is what is the fuzzy value as the output here. So we see that the output in all the cases here we are getting fuzzy. So Mamdani fuzzy model always produces the fuzzy output, and we use a defuzzifier, suitable defuzzifier, to convert this fuzzy output into the crisp value. Now what happens when for the same input x is equal to 7, y is equal to 6.5 as the crisp values, when we use max product composition? So when we use max product composition, we see that the W1 is 0.27. We multiply W1 dash W2 dash here also W1 dash W2 dash, and this is our W1 dash, this is our W2 dash, this is W1 dash, this is W2 dash. So these two outputs, when we aggregate, we are getting this as the output. So in this case here, this is the fuzzy outcome, this is the output, this is the fuzzy output, and this we can convert as the convert into the crisp value again by the suitable defuzzifier. So this way we have seen that we have discussed all the three scenarios where we have seen multiple cases with the fuzzy model, Mamdani fuzzy model with single rule, single antecedent, and again we saw all these cases with max product, max min compositions. Similarly, multiple uh, antecedents with single rule. Then we discussed the multiple rules with multiple antecedents with both the compositions, the max min composition, max product compositions, and all of these cases with the fuzzy inputs and crisp inputs. And we saw that in all the cases we always found the output in the fuzzy value as the fuzzy value, and this fuzzy value can further be converted into the crisp value by using suitable defuzzification methods. Alright, so this way we have understood as to how with certain inputs to the Mamdani fuzzy model we can get the suitable output or the corresponding output. Now when it comes to the defuzzification, so there are several defuzzification methods, but here we'll be discussing very commonly used defuzzification methods. So the first one is the centroid of area method, through which we can get the crisp value of the fuzzy value. And then we have the bisector of area, mean of maximum, smallest of maximum, and largest of maximum. So these are some of the commonly used defuzzification methods that we use for converting the fuzzy value into the crisp value. Let us discuss this one by one quickly. So centroid of area is COA, and here is the formula through which we get the crisp value when we have the fuzzy value, and we use this formula. The center of area is very simple. So ZCOA, which is the crisp value we get out of the integrating, we integrate the mu A of Z into Z, and then we have the dz, and then we have, and we divide it by the integration of mu A of Z into dz, where mu A Z is the aggregated output membership function, which means this is the output that the fuzzy output that a fuzzy model generates. So by applying this, we can get a crisp value corresponding to the fuzzy value. So this is the center of area which is used for converting the fuzzy value into the crisp value. Now, the second one is the bisector of area. So, bisector of area expression is here. This basically does nothing but when we have any fuzzy set as the output, fuzzy value as the output of the model. So what it does is basically it bisects, it divides into two, uh, um, and each of the sectors, each of the parts of this equal area. So this area is same as this area here in this case. Similarly, we have the mean of maximum. This is very simple. There is no calculation normally needed. So mean of maximum here is that we have the maximum. So we see that the maximum is here in this case. So we first take the maximum here, all the maximum, all the here the maximum portion, and then we take the mean of that. So we basically divide this into two here in this case because we are taking the maximum, the mean of maximum. So we take the maximum and then we take the mid value, and this value, the corresponding to this value, we take as the crisp equivalent to the fuzzy value that we are taking for the conversion. So this is the crisp value as the output. Then comes the fourth one here. The fourth one here is the smallest of maximum. So in this case, if we have this as the fuzzy value, so we first take the maximum um, in this fuzzy value. So maximum is here, you see, the maximum is here, this portion is maximum. So here we choose the smallest of this maximum section. So smallest of the maximum section is this, and then corresponding to this we take the output. So this output is nothing but the crisp value. So this is the crisp value. This is the crisp value corresponding to the fuzzy value, and this is fuzzy value. Okay, so then comes the fifth one, and fifth one is the largest of maximum. So if this is the fuzzy value here, so this section again is the maximum. So in this section we see which one is the largest. So largest of the maximum will lie here, this endpoint, and corresponding to this output here, the output value, that is Z, is the crisp value. So this is the crisp value if we follow this criteria. So here, when we apply largest of maximum, if we have been given this as the fuzzy output, and corresponding to this we will get the crisp output converted. So this way we have seen as to how the Mamdani fuzzy model operates for different scenarios, like we have the single rule, single antecedent, single rule, multiple antecedents, multiple rules with multiple antecedents, and then with different compositions like max min, max product, and again all of these with fuzzy inputs and the crisp inputs. And that after that we discussed the some commonly used defuzzification methods, and with this I stop here, and in the next lecture we'll continue with some examples of Mamdani fuzzy model. Thank you.